you serious? Are you serious? Folks, quickly now, I want to give you an update.
That we observe, the other bang that happened before that becomes really a little bang. That's just a precursor to the real Big Bang.
Even today, the universe is expanding at high velocity. Galaxies speeding away from each other so fast that they seem to violate light speed as the ultimate speed limit. The faster-than-light expansion of space sets yet another limit on what we can see from Earth, where the galaxies of the universe continue to rush away from us.
The galaxies that are relatively near to us, those that you can see easily, are moving away pretty fast. And indeed, the more distant ones are moving away faster. But the ones that are really far away, in fact, are moving away faster than the speed of light. And then there are the galaxies that you will never see because they started out so far away that the light from them will never reach you because the space is expanding faster than the speed of light.
Space itself, then, is the exception to the rule. It can expand faster than the speed of light. But everything inside it remains bound by Albert Einstein and his theory of relativity.
Albert Einstein is the cop on the block. You cannot break the light barrier. We physicists can accelerate particles to 99.9999% the speed of light, but we have never, ever broken the speed limit.
But we don't need to break the limit to experience the strange province of light speed. If the universe bends and stretches around the speed of light, what happens when we hit the accelerator and start to get close? For most of us, light seems simple and uncomplicated, a quality of nature by which we see the universe. Under the scrutiny of science, however, it becomes strange and bizarre.
Light is such a common thing in our everyday experience, and yet we have very little understanding of it, really. It's very weird. The speed of light is something that the entire universe bends around to accommodate.
We can begin to understand why the universe bends itself around light speed by joining physicist Clifford Johnson at a bicycle track, where a tennis ball will compete against a beam of light.
If I throw an ordinary object like a tennis ball, I can throw it at a given speed, it'll go a certain distance.
This is the path of the tennis ball as Johnson throws it while he's standing still. It lands roughly halfway down the track. Next, he'll throw the ball again, but this time from a moving bike, with different results.
If I throw the tennis ball at that same speed while riding the bike, it'll go faster because it's the speed of the tennis ball plus the speed of the bike, and so it'll go further.
Compare the two tosses, and the difference is clear. The ball goes faster and farther when thrown from the moving bike. It makes perfect sense. But now we put light to the same test, using the bike's headlight instead of a tennis ball.
If I'm standing stationary and I switch on the headlight of the bike, that beam of light that comes out of the headlight comes out at the speed of light, no other speed but the speed of light.
Suppose the beam was slow enough for us to actually see its motion down the track. We mark its position just a brief moment later. Next, Johnson switches on the headlight at riding speed, and the unexpected happens. In that same moment of time, the light travels exactly the same distance as before.
Unlike for the tennis ball, you don't add the speed of the bike to the speed of the light. The speed of light remains the speed of light.
The two light beams travel the same distance because light speed is constant and independent of the source's motion. It may fly against intuition, but it is a fact of nature. Every beam of light in the universe travels at the same speed in empty space, no matter how fast the star or comet or galaxy that emits it is moving. After scientists discovered this fact at the end of the 19th century, Albert Einstein did the math for the rest of us and developed his special theory of relativity, with constant light speed as its center.
Understanding the speed of light gave us a window into understanding the nature of space and time as we understand it now. We do not live in a rigid world where meter sticks and a clock ticking at irregular intervals. We live in a flexible, stretchy, Einstein's world, relativistic world of space and time.
In common experience, the universe doesn't seem very stretchy to us because compared to light speed, we are moving very slowly. But when we crank up the velocity, things begin to change.
As you get closer and closer to the speed of light, all sorts of strange and marvelous distortions take place.
When we say that the universe kind of bends itself so that the speed of light is always constant, it's amazing how literally that's really true. As you move closer and closer to the speed of light, your time appears to slow down to an observer that's sort of watching you go by. That's amazing.
When Clifford Johnson bikes around the track, he needs to be going about 56 million times faster than his current 12 miles per hour to get close to light speed. But suppose he could.
Imagine I were riding my bike close to the speed of light. Never mind whether that's possible or not. Just imagine that this was happening. My clock's running slow compared to the cameraman on the ground who's filming me. If I do that for a while, I'm going to age much more slowly than the cameraman who's on the ground. So that when I come back from the trip and come back and talk to the cameraman, he's actually much older than when I left him.
If this sounds like magic instead of science, there is proof in something that many of us experience every day.
A great example of Einstein's special theory of relativity and the fact that clocks that are moving relative to you run more slowly than your own clock, which is at rest, is the GPS system.
The global positioning system lets us drive our cars without getting lost.
Turn right.
GPS begins with a network of 24 satellites orbiting the Earth 12,500 miles above the surface. At any one time, the device in your car receives signals from at least 4 satellites and compares their light speed travel times to calculate an accurate location on the ground.
Drive 500 feet, then turn right.
The whole thing depends on super accurate clocks. And when the engineers designed the system, they knew the satellites would be orbiting at nearly 7,000 miles an hour. The speed is enough to slow down their clocks by a tiny fraction of a second. The engineers have factored all the relativistic time differences into the system, which gives it impressive precision.
If the clocks in the satellites are running at a different rate than the clocks down here on Earth, and you don't take that into account, you will get the wrong answer for where your car is.
Drive 0.1 miles to destination on left.
The distortion of time is only one of the strange results of traveling close to the speed of light. On the bike track, Clifford Johnson continues to push the envelope as space begins doing odd things to him and his bicycle.
Imagine I'm on my bike again, going close to the speed of light. An observer looking at me would actually see, for example, that the length of my bike in the direction of motion I'm moving is getting shrunk. Actually, the bike is getting shorter.
The effect is called length contraction, and together with time dilation, it is seen by a stationary observer while looking at someone traveling close to light speed. But Professor Johnson does get his own chance to witness light speed's weird effects. As his velocity closes in on light speed, his view of the world changes drastically.
What I'm seeing as I move close to the speed of light, straight ahead, is that the shapes in front of me are getting quite distorted as compared to everyday life. Everything is being twisted into a sort of tunnel shape, and the colors are getting distorted in various ways.
The color changes come from the Doppler effect, and the shape distortions from a phenomenon known as aberration.
The distortion is somewhat similar to what you would see if you were driving through a rainstorm. If you were stationary, you would just see the rain coming straight down if you looked out of the side of the window. Whereas if you were moving through the storm, you would see that the rain appears to be slanting towards you as a result of your motion. And that's at the basis of that warping effect that you get as you're moving near the speed of light towards objects in front of you.
In reality, we don't have to travel near the speed of light to experience the distortions caused by motion through time and space. They are with us every minute of the day.
All of the distortions that happen as a result of a finite speed of light still happen on an everyday basis, even in our everyday life, but the effects are so tiny that we can't perceive them.
Still, light speed has its other quirks in the slow-moving world, quirks we perceive very well. The speed of light may be a constant, but only in the vacuum of space. When light moves through things like glass or fluids, it slows down appreciably. If it didn't, things like telescopes and human vision would be impossible. But what would happen if light slowed down much more? If the speed of light were 0? Light speed is 186,000 miles per second. It is a universal constant, but a constant with a catch. It travels at that speed only in a vacuum.
Light changes its speed when it travels through different media. It travels more slowly through water. That's why you see refraction and bending and rippling of light when you're underwater.
Life as we know it would be very different if light didn't propagate at different speeds through different materials. For example, we wouldn't be able to see. Our eyes wouldn't work the same way.
In a universe where light moved at the same speed through all materials, we would know little of the world around us, seeing only vague blobs of dark and light. That's because our eyes depend on biological lenses to focus images on our retinas. Just like lenses made of glass, they work because light slows down as it passes through them.
Why is that? Because light is absorbed by the atoms of glass, and then they re-radiate it later. So there's a delay factor. Light hits an atom, the atom vibrates, and then sends the light package off. So there's a delay factor.
The delay factor also causes light to bend when it hits glass shaped into a lens. Bent in just the right way, light can be focused, collected, and magnified. For astronomers studying the universe, nothing could be more important.
Thank goodness light slows down when it goes through glass, because that's the reason why we have telescopes. The reason why we have telescopes is because light bends going through glass, and we can concentrate large amounts of light to a single point, and then that gives us the ability to see the marvels in the universe itself.
Light travels through the glass lenses of telescopes at about 124,000 miles per second, 2/3 of its speed through a vacuum. But some scientists are looking at making use of light at far slower speeds.
And then we have the AOs over here. They're pretty much all functioning now.
At her lab on the campus of Harvard University, Dr. Lena Howe has taken slow light to the extreme by reducing light speed to 0.
The speed of light, of course, is incredibly high. I mean, nothing goes faster than light. And, you know, the usual 186,000 miles per second. And we kind of thought, gee, that's awfully high. Let's try to do something about it. So we have a detector right there.
Howe and her team conducted their experiments in a complex laboratory filled with lasers, mirrors, prisms, and other exotic gear. It is a branch of physics where few have dared to tread.
If you can start to change things so dramatically as taking this enormous light speed and then bring it down to bicycle speed, that then you're in a completely new regime of nature. You're able to now start to probe areas, regions of nature where nobody has ever been there before.
The brakes are put on light speed inside Howe's lab by focusing lasers on 2 microscopic clouds of sodium gas, chilled to a few billionths of a degree above absolute zero. A control laser hitting the 2 clouds sets them up for action. Then, a quick light pulse shoots into the first cloud, where it is squeezed into the gas and slowed to just a few miles per hour.
The light pulse goes from being about 1 kilometer long in free space. It compresses like a concertina as it enters the atom cloud and ends up being only 0.02 millimeter in size. That's less than half the thickness of a hair. So really small, and it's so small that the light pulse actually ends up fitting totally inside the atom cloud.
Howe says the atomic imprint of light in the sodium cloud is a perfect copy, embedded in atoms, of the original light pulse. It can then be stopped in free space between the 2 clouds before moving on. When it enters the second cloud, another shot of the control laser expands it to its original size, shape, and speed of 186,000 miles per second. It is comparable in some ways to a science fiction transporter that sends people or objects through space.
So in this experiment, what we really do is we stop and extinguish a light pulse in one part of space and revive it in a completely different part of space and send it back on its way.
Since light can carry information, this super advanced technology points the way to futuristic light-based computers that bypass wires and electronic chips. Information read directly from light may be faster, more compact, and more secure than anything we have today. But the greatest vision of scientists and dreamers is to be found at the other end of the light speed spectrum. We still face the speed of light as an impenetrable wall, a speed that Dr. Einstein told us could never be exceeded. Yet history is packed with impossibles that have become realities. Will we ever, for instance, be able to reach the stars in ships that go faster than the speed of light? If so, when? In April 2008, world-famous physicist Stephen Hawking called on the human race to colonize space and make interstellar travel a long-term aim.
Spreading out into space will completely change the future of the human race, but may be determined whether we have any future at all.
The stars are so far away that interstellar travel is impractical unless we can go faster than light speed. But that's an obstacle. Einstein's theory of relativity tells us that a spaceship's mass approaches infinity as it nears the speed of light.
So as you try to go faster and faster and faster, you actually get to a point where it takes more and more energy until it's an infinite amount of energy to go the speed of light. That's impossible.
It means that travel at light speed is also impossible. Or is it? Mark Millis is one of a handful of scientists who isn't ready to throw in the towel on the subject. A NASA propulsion physicist by profession, he likes to build models of starships in his spare time, and is well aware of the giggle factor in any talk outside science fiction of star travel.
The giggle factor is actually a healthy response. It helps provide skepticism to the topic, to ask deep questions to make sure that we're proceeding correctly.
Once head of NASA's mothballed Breakthrough Propulsion Project, Millis is editor of a book that has collected the serious current research on the subject.
When it comes just to the light speed issue, there's about 36 physicists who've written articles, some skeptical, some suggesting new methods on the topic.
No one is saying that anytime soon we'll be able to have warp drive to the stars. But on a scale of centuries to millennia, it can't be ruled out.
Virtually all physicists agree it's impossible to travel through space at faster than light speed. But there may be a way to cheat by altering space instead of traveling through it.
Believe it or not, even NASA scientists are studying the possibility that perhaps we can fold space, punch a hole in space, make a subway system through space and time.
That's the basic idea behind using wormholes to actually twist space around on itself and take a shortcut through the universe. What would a wormhole machine look like? Probably huge in scale, with equipment staged perhaps on a massive number of asteroids arranged in a gigantic sphere.
It would require an enormous battery of laser beams to concentrate tremendous energy to a single point. You have to attain fantastic temperatures, the highest energy attainable in our universe, in order to open up a hole, a bubble, a gateway perhaps to another universe.
Another way of tricking space into letting us travel faster than light is the warp drive.
Miguel Alcubierre was the first one to write about the warp drive in 1994.
Alcubierre, a Mexican physicist, worked out the math for a starship propelled by warping space-time itself. Behind the ship, space-time is expanded. In front of the ship, space-time contracts. In between, the ship rides like a surfer. The ship itself sits inside a bubble, and the space around it pushes it faster than light. A successful warp drive, if it is possible at all, is probably centuries away. But in Switzerland, physicists at the Large Hadron Collider may be headed in the right direction right now.
Now, the Large Hadron Collider is an atom smasher. It's a particle collider. But it's going to get to high enough energies that space and time will actually warp and bend. We're actually practicing how to bend space in the laboratory. It's the first baby step toward a warp drive.
With the physics we now know, we won't travel faster than light speed in the foreseeable future. That doesn't mean we shouldn't try.
Even though light speed travel might turn out to be impossible, to give up without trying is just giving up.
Outside his work at NASA, Millis has founded the nonprofit Tau Zero Foundation to encourage serious research on star travel. Although few scientists are pursuing the idea actively, many agree it's worth at least the effort.
Understanding our universe is one of the most basic needs human beings have as an intelligent species. So should we pursue technologies or physics that might allow us someday to travel faster than light? Absolutely. Because we never know where this might take us. Even though we might never discover a way to travel faster than light, we might discover a whole bunch of other very useful things.
And what if science ultimately proves the light speed barrier is
Are you serious? Are you serious? Folks, quickly now, I want to give you an update.
That we observe, the other bang that happened before that becomes really a little bang. That's just a precursor to the real Big Bang.
Even today, the universe is expanding at high velocity. Galaxies speeding away from each other so fast that they seem to violate light speed as the ultimate speed limit. The faster-than-light expansion of space sets yet another limit on what we can see from Earth, where the galaxies of the universe continue to rush away from us.
The galaxies that are relatively near to us, those that you can see easily, are moving away pretty fast. And indeed, the more distant ones are moving away faster. But the ones that are really far away, in fact, are moving away faster than the speed of light. And then there are the galaxies that you will never see because they started out so far away that the light from them will never reach you because the space is expanding faster than the speed of light.
Space itself, then, is the exception to the rule. It can expand faster than the speed of light. But everything inside it remains bound by Albert Einstein and his theory of relativity.
Albert Einstein is the cop on the block. You cannot break the light barrier. We physicists can accelerate particles to 99.9999% the speed of light, but we have never, ever broken the speed limit.
But we don't need to break the limit to experience the strange province of light speed. If the universe bends and stretches around the speed of light, what happens when we hit the accelerator and start to get close? For most of us, light seems simple and uncomplicated, a quality of nature by which we see the universe. Under the scrutiny of science, however, it becomes strange and bizarre.
Light is such a common thing in our everyday experience, and yet we have very little understanding of it, really. It's very weird. The speed of light is something that the entire universe bends around to accommodate.
We can begin to understand why the universe bends itself around light speed by joining physicist Clifford Johnson at a bicycle track, where a tennis ball will compete against a beam of light.
If I throw an ordinary object like a tennis ball, I can throw it at a given speed, it'll go a certain distance.
This is the path of the tennis ball as Johnson throws it while he's standing still.